Okay. So welcome to lecture 9, the third in the neural networks topic. Some announcements. The first homework of this topic is due on Thursday, and then we'll also release the next homework on Thursday, which will be due a week later. So today we're going to talk about optimization, which means training algorithms for neural networks. So the list of things we're going to talk about, we're basically going to start off talking about what works in deep learning. Like, what do you actually want to know about? In particular, we're going to talk about the Adam optimizer, which is like probably the most popular optimizer to actually use. We're then going to talk about optimization theory, like what you should care about in theory, which is a little bit different to what you should actually care about. But in particular, I'm going to show you some models, different models of optimization, and how to prove a convergence rate for an optimization algorithm. And then at the end of the lecture, I'm going to tell you about this thing called the perturbation theory approach, which is like, it's kind of like my research. So that means like definitely be critical. Okay, so before we get going, I just wanted to show you this slide again, which was from the first lecture of the topic, which is about kind of like the stages that theory should go through. And in like optimization algorithms for neural networks, most of the things that work like sort of fall into this camp of just like things which people have tried experimentally and then found to work, and then they're always based on some kind of intuitive ideas about how things work, but it's usually not like super rigorous. So that's what then I want to claim that the place that optimization theory for deep learning is at it's like we're still at this modeling stage where we like need to build good models. So that's just a perspective that you could keep in mind throughout the lecture. Okay, to begin with, like what works. So usually when people introduce like machine learning or deep learning, they tell you about stochastic gradient descent. So what is this? The idea is that we have a loss function, which I'll use this letter for, and this is a sum over data points of the loss on a particular data point. So Li is like the loss on data point I if the parameters are set to W. If we could get it, we'd really like the full gradient, or like the true gradient, which we can illustrate like this. And this decomposes into the sum over the data points of the gradient on each data point. So if we could have that, we would really like it. And in this lecture, I'm going to use a shorthand for this. I'm going to call this G to mean like the gradient evaluated on all the data. But unfortunately, this involves summing over all the data. So we'll settle for the stochastic gradient. And the idea is that this is just, it restricts the sum to be over something called a mini batch. So B is going to refer to a random mini batch of data points. Here it's like referring to their indices. But we just restrict the sum to what's called a mini batch. And the idea is that we'll randomly sample this mini batch at every iteration. So that's random. And the shorthand is, I'm going to call this G tilde to mean that this is a random estimate of the full gradient. Now, what stochastic gradient descent says is that we should update our parameters like this. So we just subtract the gradient multiplied by the learning rate, which is just a small positive number. But as we mentioned before, we don't know how small eta should be. And there's actually a bigger, so this, okay, and this is called SGD, stochastic gradient descent. There's a bigger problem with this approach than even just not knowing how to choose the learning rate. The bigger problem is that sometimes it just doesn't work very well. So, and other optimizers work much better. So this example is for training a transformer on a machine translation task, translating between English and German. And what this plot is showing is training perplexity and validation perplexity. So training on the left and validation on the right. And perplexity is just an accuracy measure. And it shows that as training progresses, as epochs increase, meaning as we've seen more and more data, how does the performance change? And the thing that we're illustrating here is just that SGD is like, on this problem, is like really unstable. Like it doesn't train very well. Like it's quite bad actually. Whereas Adam, this other optimizer, is the purple curve. It trains much better and it's like stable. And so SGD is the thing that you're often introduced to, but in real machine learning problems, it often doesn't work that well. And it's not clear why. So this beginning part of the lecture, I'm gonna like just tell you about Adam, and a good way to understand what Adam is. Well, first of all, Adam is an optimization algorithm, but a good way to understand what it is to like follow the history of its development. So it started really with this rprop method, which is another optimizer from back in 1993. Then in Jeffrey Hinton's Coursera class, they introduced a new method called RMS prop. So there's actually no paper on RMS prop, but it's like a really popular method, but it's just like introduced in like a particular slide of a Coursera class. And this RMS prop develops rprop a little bit, and then Adam develops RMS prop even more. And that Adam is, I guess, from 2015. So let's go through this like sequence of ideas. So rprop, what is it? Well, if we go back to SGD, or actually, so what Hinton says is that rprop is a full batch method, meaning you assume that you're not doing stochastic gradient, that you have the full gradient. So the comparison point is gradient descent, which says that we take our parameters and subtract the learning rate times the gradient. Now, what rprop says is, can we trust like the scale of this gradient to contain useful information? Like, does how large the gradient is matter? And it's not clear what the answer to that question is, but rprop says it doesn't matter. And what it does is it changes this update to send W to W minus, and then it acts component-wise on the gradient. So it subtracts a learning rate for the first component times the sine of the first component of the gradient. A learning rate for the second component times the sine, and all the way, and so like this, up to the last component. So what I'm saying is, like, I'm not really telling you any more than rprop says you shouldn't use the scale in the gradient, and you should just set every component of the gradient, you should only retain the sign. If it's positive, set it to +1. If it's negative, set it to -1. And then it also has a rule for setting a kind of component-wise learning rate. So it has a different learning rate for every component, but that's not important for the discussion, so you don't worry about that detail. But it's not clear why we should throw away the scale of the gradient, but rprop says we should. And right. It takes the component-wise gradient sign. And right, presumably at the time back in the 90s, they showed this had some kind of nice properties. But hopefully later in the lecture or at the end of the lecture, we're going to see a kind of what I think is a more principled reason for why we don't care about the scale of the gradient. But for now, just this is what R prop says. So RMS prop evolves this algorithm in a particular way. So what RMS prop says is that, well, R prop was assuming we have the true gradient, but really we just have the stochastic gradient. And in Hinton's Coursera class, he basically says, if you do R prop with stochastic gradients, it doesn't work anymore. So you need to adapt it if you want to use stochastic gradients with R prop. And he says that the problem is, the idea of stochastic gradient descent is that if consider a particular weight, consider one weight in the network. Let's say it gets lots of small gradients, which like pull it in this direction. Like, let's say 4 gradients in a row tell this weight to move towards the right. And then on the 5th step, it gets a really large gradient that pulls it back. Well, what Hinton says is that when you're doing stochastic gradient methods, you want, this can all be noise, and you want that noise to cancel out over a sequence of steps. So if you get lots of little gradients and one big gradient pulling you back, you want the weight to end up back where it started. But since R prop is like snapping everything to plus or minus 1, what would happen instead is it would go +1, +1, +1, +1, and then just -1. And you wouldn't end up back where you started. You would end up like all the way over here. So he says that, okay, so what Hinton wants to do is he wants to design an optimizer that has 2 properties. The first property is that it throws away the scale of the gradient. Just like R prop did. But the second property is that he wants it to retain relative scale information between consecutive gradients, or between consecutive stochastic gradients. To avoid this problem, so that things average out nicely, because if you average signs, it doesn't average out nicely. So if you think that you can write R prop like this, so you can write it roughly as W minus eta times the sine of G, which is equal to, well, the update is just minus eta times the sine of G, which can be written as minus eta times the sine times the gradient divided by its absolute value, and doing that division component wise. So this is a way of rewriting the sign of the gradient is just something divided by its magnitude. Well, what he says is basically, instead of using the magnitude at the current time step, use a running average. He says use a running average of the magnitude, because that still captures the general information about the average scale of the gradient. So you're dividing out the scale, but the number that you're dividing by, if you divide by a running average, doesn't change much from one step to the next. So you still retain relative scale information. So to write that mathematically, RMS prop says that your update is minus eta, the learning rate, times G, divided by the root mean square estimate of G. What does root mean square mean? Well, it's just a running average of the magnitude of G. But to write out the formula for that, RMS of G is you basically take G at the current time step and square it. You add beta times G at the previous time step squared, where beta is a number between 0 and 1. And you add beta squared times G at 2 previous time steps squared. And this builds up a kind of exponential running average of squared gradients. And then you keep summing over iterations in this formula. And then you basically then take the square root. And this is a root mean square running average. And technically you also have to scale by 1 minus beta to get the normalization constant of the average, right? But the idea is that the running average captures the scale information, captures how large the gradient is typically, but from one step to the next, the running average doesn't change much. So consecutive iterations are divided by a similar number. So it has these two properties that it throws away scale information. We're still not sure why we want to do that, but that's what our prop said. And it retains relative scale information, which is useful if we have stochastic gradients, because then we can hope that noise will average out properly. Once we have RMS prop, there's just one more step to get Adam. So RMS prop says that we're doing this, and all Adam says is, well, if we're estimating the divisor of this thing by running averages, why not also estimate the numerator by a running average? So Adam compared to R prop is basically just take a learning rate. You take a running average of gradients, which by EMA, I mean exponential moving average. So I'll write a formula for that. And then divide by root mean square of the gradient. So Adam is just RMS prop with some extra smoothing. What does EMA mean? It says take the gradient at the current time step and then add beta times, and actually it uses a different beta for the numerator. Take beta times the gradient at the previous time step and beta squared times the gradient at the 2 previous time steps plus dot. So it just takes a running average of gradients. So it somehow smooths the gradient. And this is the technique which is like just used, like it's so useful, and it's used like pretty much, it's like if you do machine learning or deep learning 101, it's like one of the first things you'd learn about. But you can tell, like something which I'm hoping is coming across is it's not like super rigorous, or like it's kind of like there's some jumps or leaps of faith, or like you might have certain questions like, why do we want to remove the scale of the gradients? Those would be good questions. But okay, I'm gonna stop briefly and ask if anyone has any questions so far.
I have a question.
Yeah, please.
So how does like Adam as it compare to like other type approaches, like say momentum method and stuff? Like what is the practical, and like maybe if anyone had like any like theoretical benefits to Adam over like other methods?
Right, okay, so if you Google like theory of Adam, you'll find a large number of papers. But it's still not agreed. So there's no real consensus. Like I'll give you my point of view maybe towards the end of the lecture, but yeah, there's no clear-cut answer. In terms of comparison with momentum methods, this exponential moving average of gradients that appears here, that's basically the same thing as momentum. What momentum does is it keeps a running average of gradients. So that is momentum. There's lots of theory about like why momentum helps, but it's usually based on, for example, like convex models and this kind of thing. So it's not clear that those theoretical explanations are actually why it's helping in deep learning. But that's what I mean. If you Google theory of Adam, for example, you would find like connection. People would say, well, momentum helps because of the fact that momentum helps in convex optimization. But that's a logical jump, which is not obvious. Yeah. So at this point in the lecture, I'm not even going to try and give you rigorous reasoning for this stuff.
Hey, Jeremy, can I ask a question?
Yeah, please.
In the first lecture, you said inductive bias is important in deep learning, like different tasks need different architectures, like computer vision has its canonical models, NLP has its canonical models. So right. I'm wondering whether it's true for the optimizer, for the choice of the optimizer, like the Adam is best. Is that just in the sense of some particular task? Or in other words, do we expect different optimal optimizer for different tasks, like for computer vision, for NLP, for regression? Yeah.
Right. So certainly it's empirically true that in different tasks, people use different optimizers, and different optimizers get different performance on different tasks. But whether that's because of it's not clear why that is the case. But the claim I want to make is that if you look at these plots and you see that SGD is super unstable, whereas Adam trains quite stably, you usually don't see the inverse of this, where SGD trains really stably, but Adam is unstable. Adam is generally reliable and trains well on almost all deep learning problems that I'm aware of. Whereas it's SGD which sometimes works and sometimes is super unstable. So I think this is why Adam is so useful and so well known and this kind of thing and so popular, is because it's actually quite reliable. Although there are some problems where it gets slightly worse performance than SGD.
I see. Can I see the optimizer is seems more, you can use it much more broadly compared to a neural network architecture.
Sorry, are you saying, is that fair to say?
Right. Yeah.
Yeah, I think that's fair to say that Adam works in, training GANs, training transformers, training image classifiers, training, it's pretty much the go-to optimizer. As soon as you get away from image classification, it's the most popular optimizer for reinforcement learning.
Thanks. Yeah, gotcha.
But okay, in the stuff about inductive bias, I'll try and get to that when we talk about generalization theory, but yeah, for now, let's keep going. So there's this quote in this green box from Hinton in his Coursera class in 2012, where he says, "We really don't have nice, clear-cut advice for how to train a neural net. And then think how much better neural nets will work once we've got this sorted out." And I would argue that the only real clear-cut advice is Adam seems to work pretty well, but he was pointing out that sort of deep learning relies on a large number of tricks that aren't super well motivated, and I think that that's still the case. And what this image is showing is just a subset of all the optimization algorithms which have been proposed since, most of these are actually within the last year or two. So it's there's no consensus about what the right even optimization principles are for deep learning. And there's just so many optimizers being proposed. And it feels like we're kind of still in this state that we don't quite have it sorted out. What are the right principles?
I have a question.
Yeah, go ahead.
Which is, I don't know if you're going to maybe when you present your theory at the end of the state of the world, but maybe because it's so general, there's there is no, are you optimistic about this? That it's possible, or is the fact that we're trying to approximate all functions with like one algorithm, kind of like, you know.
I'm optimistic, and like basically the optimism is like, I think that, well, essentially if you have an optimization theory, it should be based on like the structure of the functions that you're trying to optimize. And neural networks do have like, you know, like a simple structure. You have matrices, you have nonlinearities. The structure isn't that complicated, but it's just like the optimization theories people use have basically nothing to do with that structure. So like, I think that like my personal opinion is that when they actually address that structure of like, even just like the structure of the fact that you're dealing with matrices is like a good place to start. But people just use, many papers use very generic assumptions like Lipschitz smoothness, which doesn't even address the fact that you're optimizing over matrices.
Okay, thanks.
Yeah, I guess it's important to bear in mind that I have, you know, like strong opinions about this topic. So take what I say with a grain of salt, because like, yeah. I don't want this lecture to be like the indoctrination process, because it is related to my research and it's easy to just indoctrinate people with your own ideas. So yeah, be a bit suspicious of me.
Hey, Jeremy, I have a question about the gradient. So kind of unrelated, but I was wondering if it's possible to get kind of a bound on the gradients for a network given a loss function.
Okay, great. Okay, let me do the next section on optimization theory, and then if you still have this, or well, let's just do the rest of the lecture, because that's kind of what we're getting towards, is like that kind of question.
Yeah, for sure.
Okay, so now we're going to look at optimization theory. In particular, I'm going to show you some different models of optimization, and I'm going to show you how to prove a convergence rate under one particular model. So optimization theory relies on models of smoothness, especially first order optimization, which is what we're doing. We want to know how smooth is my function. What does that mean? So what I'm illustrating here is I'm imagining that we have a loss function and it depends on a one-dimensional variable. So we're doing a one-dimensional optimization problem. And we know our current parameter value W, and we've evaluated the gradient at this point. So we know that locally the function looks like this. Well, what we really want to know, if we want to like pick our step size for gradient descent, is whether the function, you know, as we move away from this point, does the function kind of like behave like one of these functions? Or, you know, what's the alternative? The alternative is kind of like, you know, as we move away from this point, the function could vary much slower, if this makes sense. It could like vary like one of these functions I'm trying to illustrate. And the point is that if we're in this category, then we can use a much larger step size, because the gradient is going to be reliable for much longer. Whereas if we're in this category, we need to take smaller steps. So basically the optimization algorithm that we get needs to know about this smoothness property. And if we don't know anything about the smoothness property, we're going to end up like tuning our step size a lot, which is what people are doing in practice in machine learning. Is you often have to be quite careful about how you set the step size. So now I want to try and phrase this discussion in words rather than in pictures. So the question is, one way of phrasing this question is, how fast does the gradient change as I move away from a point? You know, like I start at this point and I move away, how quickly does that gradient change? That's a way of formalizing what smoothness means. Another way of phrasing this is, how far can I trust the first order Taylor expansion. So what does trust the first order Taylor expansion means? It means that when I'm in this region, the linearization of the function is valid. But if I move away, it becomes invalid. Like, how far can I move before the first order Taylor expansion becomes invalid? And that, if you think about it, these are the same question, because the gradient uniquely determines the first order Taylor expansion and vice versa. So this is like the core question of first order optimization. Like, how fast does the gradient change? Or another way of saying that is, what is my model of smoothness? Okay. So just to tell you again what I mean by Taylor expansion, I imagine I have a loss function, and it has, I evaluated these perturbed parameter values, so W plus delta W. And this, but like, you know, if assuming the Taylor series exists, it's equal to, you know, the gradient transpose the perturbation size. That's the first order Taylor expansion. And then, you know, there's higher order terms. Like the next one is like, H is the Hessian, which is the matrix of second derivatives. And then there's even higher order terms. So just to remember that in the shorthand we're using, G is going to refer to the gradient. H is the Hessian, which means the IJ component is like the second derivative of the loss with respect to Wi and Wj. So from this perspective, the question that we're asking is, how large can I make delta W before, you know, like all of these terms start to dominate these terms? And we're going to show you various, I'm going to show you various models that optimization theorists have of answering this question. So the first model is Lipschitz smoothness. So what this says is that the perturbed loss is bounded by first order Taylor expansion. And then now we're going to introduce the model. And it says we're going to have this structure. So by the way, Frobenius norm is just like the sum of squares, the sum of squared entries in a matrix. So what this model called Lipschitz smoothness says is that we're going to model the breakdown in the first order Taylor expansion with a quadratic penalty. And L is a constant which we're allowed to set. And the larger we make L, the faster that quadratic breakdown is, or the stronger that quadratic is. So if you think about what that means in terms of that picture we drew earlier, where we have like this local linear part of the loss function, it's saying that the breakdown, as we move away from here, we're going to model it as kind of looking like a quadratic. But there's no reason why it really should be that way, but that's our model. Okay. The point, I think the next thing I want to say is that under this model suggests that under this model, the best optimization algorithm is like vanilla gradient descent. So to see that this model implies gradient descent, what we do is we differentiate the right-hand side with respect to the size of delta W in order to minimize, you know, what we're trying to do is, what we really want to do is minimize the perturbed loss, but we don't know what this is. We just know the model of it. So we're going to minimize the model. To minimize it, we differentiate and set the derivative to 0. And we find that differentiating with respect to delta W, we find that G plus L times delta W equal, and we set that to 0. And we find that delta W that minimizes this model is equal to -1/L times G. So that says that the optimal perturbation, delta W, is the negative gradient multiplied by a step size of 1 over L. And the interpretation of this step size is that the larger the quadratic penalty is, the smaller the steps that we should take. So what I've shown you is, given a model of smoothness, how can we derive an optimal optimization algorithm? And for this simple quadratic penalty, we get gradient descent. But you already get a sense that if we did not have a simple quadratic here, we might get a different algorithm, which would not only potentially have a different step size, but it might even tell us to move in a different direction. So that's like the general flavor of stuff in optimization theory. What I'm going to show you now is how to derive a convergence rate of an algorithm. Does somebody have a question?
Yes. Can you go back to the last slide about Lipschitz smoothness? Is that also? It looks very similar to like another definition called like strongly smooth. Are those like similar?
Yeah, I mean, do you mean like strong convexity has some kind of assumption about that it's like you have the convex condition and then you have an extra quadratic thing?
Yeah.
There's some connection, but yeah, it's not so important for now, but yeah, there's a connection. Yeah. Okay. So how to derive a convergence rate? Well, let's fix our optimization algorithm to be the thing which is, so we're still working in the Lipschitz smooth model, which I wrote at the top, and we're going to fix the optimization algorithm to be the thing which was optimal under this model. And in particular, the perturbation at the kth step of the algorithm, we're going to set to, you know, like the gradient at the kth step. So what that really means is like minus 1 over L times the gradient of the loss when the parameters are set to their value at the kth step, because we're running an iterative procedure of updating the parameters iteratively. So the first step is we're going to measure the improvement of the loss under one step of the algorithm. So what we say is after one step, you know, we update the old parameters were, well, the new parameters are WK plus 1. The old ones were WK, and we subtracted 1 over L times the gradient. So what's the improvement? Well, we want to measure the difference between the loss at step K plus 1 minus the loss at step K. This is how much the loss improves in one step. And we can bound this using the smoothness model by, you know, what we're going to do is we're basically noticing that the two terms that we've already written down appear here and here. So we're going to bound these terms in terms of the terms that we haven't written down. But we're going to plug in delta W is minus 1 over L times GK. And we're going to find that this thing is bounded by minus 1 over L times the norm of GK squared plus L over 2 times 1 over L squared times norm of GK squared. And then we're going to realize that these terms can be combined into the same term. This is equal to minus 1 over 2L times the norm of GK squared. So the interpretation of what I've written down is that the improvement of the loss in a single step is bounded by something which just depends on the norm of the gradient at that step. Meaning that what it says in words or intuitively is that the larger the gradient is, the more improvement I can make in a single step. The next step of the proof is to sum over iterations to get if we sum the improvement in one step over iterations, then we get the improvement over all steps. So we sum this thing over iterations. And what we realize is that so we're going to sum from step 0 to step k equals capital K minus 1. So now capital K is the total number of steps that we're running our algorithm for. And if we sum this inequality that we wrote down, we find that the total improvement is, well, you notice that when you add up all the terms on the left-hand side over K, you get a lot of cancellation because this term will cancel this term in the next term in the sum. So you're going to get like L of WK, W capital K minus L of W0. So all those other terms that we added up just cancelled out, is less than or equal to the sum from K equals 0 to capital K minus 1 of minus 1 over 2L times like the norm. So that last term is just summing up the right-hand side of this inequality. Okay. And then the next observation is that if I assume my loss function is positive, which, like, you know, in practice it usually is, or it basically always is in machine learning, then we can bound the total improvement has to be it's confusing because the inequality is like the sign is flipped from what you would want to include, but basically the intuition of what this is saying is that the total possible improvement I can possibly make is smaller than the loss function at the initial step, because I can't make the loss smaller than 0. So the loss at step 0 is a bound on the total possible improvement. That's what this inequality is saying. Once I have that, you know, this minus sign cancels, we can cancel that with this minus sign and flip the inequality. And we can like rearrange, and the final result says that, and we can divide through by K. We're free to divide this inequality through by the number of steps. And we rearrange and we get that this is the final result. So what this says, this is we're going to think of this as being a rate of convergence of the algorithm. And the idea is that the left-hand side is the average norm of the gradient over the trajectory of my optimization run. And what the right-hand side says is that this decays like some constant divided by the number of steps. So as I increase the number of steps, I must encounter a place where the gradient is small. So that's the guarantee that we're getting for this optimization method. But notice, okay, yeah, it's not super important that you follow this for the rest of the lecture, so don't worry if you got lost. But basically, you know, we could prove something, but it depends really intimately on our model. And if we have a different model, then this proof wouldn't hold anymore. So this is called a deterministic convergence rate because I assume that there's no noise in the gradient. I just want to quickly show you how the result gets modified if the gradient is noisy, if we're doing stochastic gradient descent. So all I changed is I use exactly the same algorithm with exactly the same step size, but I assume that instead of the true gradient, I have a noisy estimate of the gradient. And I assume I have a model of the noise, which is that the average noisy gradient is equal to the true gradient, and that the total variance of the noise is bounded by sigma squared. So this is called like an unbiased noise model with a bounded variance. And if you do a stochastic analysis, which is on the web page, I'm not going to do it. It's in the slides on the web page, but for now I'm just going to tell you the result. You get a different convergence rate. And so what this is saying is that instead of the average gradient norm appearing on the left-hand side, average over iterations, we get also the expectation over noise. So because there's noise, anything could technically happen, but we can still make statements about what we expect to happen. So that's what this bound is doing. So we've modified the left-hand side by adding an expectation. And then the right-hand side appears, this term is the same. So it says that as we ramp up the number of iterations, capital K, we're going to converge to a place where we expect that the average gradient over iterations must be small, meaning we must converge to a place where the gradient is small in expectation. But we have this term which is actually preventing the gradient norm from going to 0. We only get convergence to a kind of noise ball of sigma squared. To give you the intuition of what's going on, imagine that this point is the minimizer. Then there's like what this says is that under this algorithm, the optimizer kind of converges to this minimizer, but then it just stays in this ball around. It can't quite settle down because of the presence of the noise. And notice that we use the constant step size in our algorithm. So if you wanted to get around this problem, you would actually have to decay the step size at the end, and then that would allow you to get around this problem. But this is just showing you the kind of form of a convergence rate for a stochastic algorithm. So now we're going to move on from convergence rates, but I just wanted to show you that they exist. So the next thing I want to show you is a different model. So here I've written the Lipschitz smoothness model, which we just talked about. There's another model called cubic regularization. And what this says is that the loss, the perturbed parameter value is bounded by, instead of the first order Taylor expansion, we put the second order Taylor expansion. Okay, so that plays the role of the thing in the purple box, the second order Taylor expansion, and then we need a penalty. So we penalize it with a cubic term. Okay, and we call this model of the optimization landscape. We call this the cubic regularization model. So it's like, we just took things up one order. That's cubic regularization. You can see there's pros and cons. Like the pro of this model is that it uses more information about the function. It uses the Hessian information, the second order information. So assuming the Hessian exists, it's a better model. The con is that for neural networks, the Hessian, it's a matrix, and the number of elements in that matrix is the square of the number of parameters. So commonly we'll have neural networks with billions of parameters. So you can't even fit that Hessian into the memory of the computer. So this is like the kind of the idea of why in deep learning you prefer to use first order optimizers rather than this like second order model. The next thing I want to show you really quickly is another model, which is called mirror descent. And this is going to be on the next homework. So you'll explore it more then. The idea of mirror descent is we say, well, we're interested in like the breakdown of the first order Taylor expansion. So mirror descent says like, what do we need to put here to make this an identity, to like make this really inequality? Well, we need to add, if if this thing appears on the left-hand side, we need it to also appear on the right-hand side. So we just add that. Okay. And this thing appears on here, but it doesn't appear on the left-hand side. So we better subtract that. Okay. So this is an equality just by construction. Now what mirror descent says is that, well, I actually don't know what this is, what this term is, because it involves this, and right, this is the thing that I cared about all along. So I don't know what this is, but what I'm free to do, because there are no rules, is I can just pick my favorite function h, and I can replace this with the same thing, but for h instead. So I can write h of w plus delta w minus h of w plus a gradient of h transpose delta w. So my, and like, this is my model. This, like, my model is this thing plus this thing. And if I can choose h however I want, and if I choose a different h, I'll get a different model. And you can see that somehow, if we want this to be a good model, we want to choose h to like somehow mimic some interesting property of the original loss. But h can be a really tractable function, whereas our loss can be a really complicated function. So this is called mirror descent. And I'm like, actually, you're going to explore that on the homework. So, and there's more info about it in the slides. But I'm just going to, I think I'm a bit short on time. But the thing which I want to tell you is that gradient descent is a special case of mirror descent. So what that means is, remember that this is the thing, this is the important thing in mirror descent. If I pick h, one thing I can do is I can pick h to be just quadratic, to be the norm of w. If I do that, well, the h of w plus delta w is equal to this thing. And the basic claim is that, you know, I plug a quadratic h into this, and I find that this thing just becomes equal to the norm of the perturbation. And remember that this is the thing which appeared in the Lipschitz smoothness model. We just got a quadratic penalty. And that, remember that that implied gradient descent. That was what we showed a few slides ago. So the idea is that for a particular choice of h, mirror descent gives you gradient descent, but you can choose other h's and you'll get other optimization algorithms. Okay, so that's gradient descent as a special case of mirror descent. So what's missing? Like that was the section on optimization theory. You know, like we didn't really talk about things which, well, yeah, what's missing from this theory? Like, why is it not applying to neural networks? So, you know, there were the second order methods that involve the Hessian, where they don't really scale to neural networks because the Hessian is too large, like has too many, it's got all pairs of parameters in the Hessian. So mirror descent, typically people use mirror descent with convex H functions, but there's kind of something non-convex about neural networks. So it's not really clear whether we're going to be able to model them well with convex, even locally with convex functions. So that's something that's a bit unclear about mirror descent. And the main thing I want to point out is that these techniques we just talked about are kind of generic. We didn't talk about neural networks. And it's not clear how to, you know, whether we can shoehorn neural networks into those optimization frameworks or not. Yeah, if like now's a good chance to ask questions, but because we're about to move on to the next topic.
I have a question.
Yeah, please.
About the Hessian large-scale Hessian computation.
Yeah.
I think you've been like mentioning how there's like, I don't know, like the topology kind of the parameters is somewhat, you know, not leveraged. If you basically assume that a bunch of the parameters in the Hessian were 0, would that like open up something like for instance, I think Joel Trop does like sketchy SGD, and I don't know exactly, I didn't follow exactly what it is, but I know he's working with like huge matrices by like exploiting sparsity basically.
Right.
Is there any, I don't know, thoughts on that kind of approach?
That's a great question. It's not clear that the Hessian is particularly sparse for neural networks. Like I haven't looked at that question like in any depth at all, but you know, if a component of the Hessian is 0, it sort of says that like that parameter, there's like no real curvature with respect to that parameter. But at least my intuition about neural networks is that kind of like all the parameters are somewhat equal. But and that it's not obvious that it has this kind of sparse structure. But yeah, I haven't looked at that, and that's a good, if anyone wants to look at that question in the final project, then that's a good thing to look at. But that's a great idea, and those are the kinds of things you would want to consider. Is like what structure does the problem actually have? If that is the structure that it has, then yeah, that would be great.
And something that I didn't quite follow would be, how much does that Hessian really buy you in terms of getting out of a non-local method, right? Like, is it, you know, tremendously
it can potentially
different?
it like what Nesterov showed is that this method called cubic regularization has a better convergence rate than gradient descent, meaning that if you have that Hessian and it's cheap to obtain, then the optimization method under the model that he considers can actually converge much faster. So it can, like, knowing more information about the function can help a lot. But you always have to remember there's a trade-off because computing the Hessian is expensive. And B, you know, that cubic regularization model, there's no reason to believe that a priori that it's a good model of neural networks. Right, like some of the basic problems are that like neural networks aren't even twice differentiable because, you know, like there's a nonlinearity which has a discontinuity in its gradient. So like there's a lot of subtleties when you try to apply some existing framework, just like second order optimization to neural networks, because it doesn't perfectly fit into the assumptions of those models. So to an extent, these are some of the things I thought about a lot during my PhD. So the next section of the lecture is just like the answers that I came up with, but you know, like, yeah, be critical of what I say next, I guess, because yeah, and I would welcome the criticism, or I would like to think that I would welcome it, but I might actually respond, you know, like no, you guys are wrong. But I'd like to think that I would welcome the criticism. But anyway, let's continue.
May I ask a question before you go to the next section? So
yeah,
I see that in your like derivation and in homeworks, you use like Frobenius norm a lot. Is there a particular reason? Is it because it's like easy to evaluate or something? Like,
yeah, I made an effort to put things in terms of Frobenius norm just because under the assumption that things are well conditioned, then it's sort of like the best norm. But that's not a really rigorous statement, but
I mean, why is it the best norm? Like, is it?
Well, it's not worst case. Like if you use a spectral norm, you're really thinking about worst case properties of the matrix, because the spectral norm is a max over singular values, whereas the Frobenius norm is the root mean square singular value. So you can think of it as if the matrix is well conditioned, then there's the Frobenius norm is sort of capturing the nice average properties of the matrix, whereas spectral norm is worst case.
I see.
That's not super rigorous, but like that's the spirit of like when you would want to use a Frobenius norm over other kinds of norms.
I see.
Like I just think that the Frobenius norm is probably the norm you would come up with if you had to invent your own matrix norm.
Yeah.
At least it's the one I would come up with rather than the spectral norm.
Yeah, thank you.
Okay. So the starting point for this section is like, yeah, there's these things in the homework about these perturbation bounds. So going back to lecture 7, this is what we showed. So what we did was we assumed that we're dealing with a deep linear network, which was just a product of the weights are A, and it was just a product over the components of A times an input. And the claim was that this is the simplest approximation of a neural network that has some degree of reality. Like it involves products, whereas the neural network involves compositions. And we showed that this obeys this exact perturbation result. The other thing I want to point out is that the derivative of this function with respect to one of the parameters has the same basic form. Taking the derivative just knocks out that component. So this would be the product over I not equal to j of ai times x. So the claim so far is that the function and its derivative have the same mathematical form, and the relative perturbation structure of that mathematical form involves products over relative perturbations to the parameters. So the thing on the left is the relative change in function, and the thing on the right takes a product over parameters of the relative change in each parameter plus 1, and then at the ends there's a minus 1. And then, right, you could imagine now deriving the analogous result for this thing, and you would get that the relative change in this thing, you know, it looked exactly the same. It's just you would get the product over I not equal to j. Like you would knock out one of the terms in the product. Okay, going back to Taylor expansions. So like, what does that have to do with optimization? What do those perturbation bounds have to do with optimization? So we're interested in the region in which this thing is valid. And in particular, we care about like how far can we trust this gradient? So remember that G, what we mean by that is the gradient with respect to the weights of the loss. And by the chain rule, this is equal to the, you know, it's the gradient of the loss with respect to the network output times the gradient of the network output with respect to the weights. Okay. So we've decomposed G into 2 terms, but the second term, we have a perturbation bound for that thing, right? We just argued that so what we're really interested in is G as a function of delta W. So by this, we're meaning the gradient of the weights evaluated at the perturbed place. And like, what we want to know is how quickly does this gradient change as we vary delta W? So we can measure that by taking like the norm of the change in the gradient as we change the parameters, dividing it by the norm of the original gradient. Okay, and maybe we can just put a Frobenius norm. So, okay, we're interested in, to know how quickly how far we can trust the Taylor expansion, we're interested in the relative change in the gradient. But the gradient like involves this term, and we know that the perturbation of this perturbation structure of that term involves this kind of product over relative change in each parameter. So that, like, the idea that we have is just to model this thing as being bounded by something of that form, which I just showed you. So the product over layers of the network of 1 plus the relative change in that layer in layer L, and that's a Frobenius norm, divided by the norm of the parameters in layer L. So this is our model. Like, we showed you the other models involving like quadratic penalties and mirror descent and this kind of thing. We're saying that this is a model which has some reflection of the structure of the network, because we're saying bound the relative change in the gradient by a product over layers of the amount of relative change in the layers, the amount of relative change in each layer of the network. So it reflects, you know, the model reflects two aspects of the network. The model is aware that the network is constructed out of a layered series of matrices, and it is aware that also those matrices are composed together. So that's why we see a product. So this is the model. Once you've set up a model, you can go about deriving optimization algorithms. So what we say is that a principled way, or a more principled way of designing a deep learning algorithm, is to minimize the first order Taylor expansion, subject to the constraint the product of the relative changes over layers is small.
Can I ask a question here?
Yeah.
Maybe I missed this earlier, but what about the nonlinearity?
Great question. So we've totally neglected that. But so one argument for doing that is, you know, if you can't, well, one argument is if you take away the nonlinearity, a neural network is just a big product of matrices. So you should at least know how to optimize a big product of matrices, because things are only going to get worse once you introduce the nonlinearity. So that's one argument. But that's a great point. That the model neglects the nonlinearity.
Okay, gotcha. Thanks.
But it's not clear how much the nonlinearity changes things. But yeah, it's a good point. You know, the nonlinearity is somewhat linear if it's a ReLU, but yeah, but it's a great point. All models are wrong, some are useful. That's my defense, but it's not clear yet whether this is a useful model.
Maybe this is an unfair criticism, or you're going to address this, but if you take away the nonlinearity from a neural network and it's a big product of matrices, isn't that just a matrix?
Yeah, but the structure of a product of matrices is like, it is equivalent to a matrix, but it has a very different mathematical structure. Right.
Okay, so that was the distinction I wasn't picking up on. Is that you're trying to, like, I guess, an approach to multiplying matrices that maybe you don't have the, I guess, this massively dimensional matrix that you're trying to optimize, but more how you building blocks.
Right. Yeah. Like,
make it.
Yeah,
Okay.
Exactly. If you had to optimize over a big product of matrices, and you weren't allowed to just collapse them all into one matrix, like, how would you even do that? And like, this should tell you something about that. Yeah. Yeah, right. Like, one matrix has a very much like a convex structure, like it turns into a convex optimization problem, but optimizing over a product of matrices is not a convex optimization problem. Obviously, you could make it convex just by collapsing the product, but but that would take you further away from what the neural network is. Don't worry if that didn't make sense as well, because it's not important. Okay, so what's the simplest algorithm that makes small relative updates? Well, the idea is that this term tells you that you want to be somewhat aligned with the negative gradient. And this term tells you like how big the update can be. So basically what I want to claim is that the simplest thing is that for every layer, set the size of the perturbation to that layer and the norm of that thing divided by the size of the weight matrix in that layer. Sorry, there should be an L here. Okay, set this to be equal to eta, where eta is what we're gonna now mean by the learning rate. So for us, our learning rate is controlling the relative size of the perturbation per layer. Does that make, so if eta is 0.01, that means that my optimization method is allowed to change every weight matrix by 1% per iteration. So it's a relative update rather than an absolute update. Okay, so an example of a way to make an update which satisfies this property, that the relative change is equal to eta, is to set, for every layer, set like the new value of WL is going to be like the old value minus eta times the gradient divided by the norm of the gradient times the norm of the weights. So does this make sense? That if what this is saying is take the gradient, remove its scale, and then reintroduce the scale of the weights, then the relative size of this update is eta. Like if, yeah, to see that the relative size is eta, like, let me just compute what is the relative size of this update. So delta W is equal to minus eta times the gradient divided by the norm of the gradient times the norm of the weights. If I take the norm of delta W, then I basically take the norm of G on the right-hand side, and I find that this cancels. And I get that the norm of delta W is equal, right? This becomes positive. I find that the norm of delta W is equal to eta times the norm of W. So if I divide through by the norm of W, then the relative size of the update is equal to eta. So basically, what I'm claiming is that this is the simplest optimizer, which is aligns with the negative gradient, but makes small relative change per layer. Okay.
Hey Jeremy, are you basically saying the magnitude of gradient does not matter, but the magnitude of weight matters?
Yes, that's, and okay, yeah, great point. And that's like, remember at the beginning, I was like, R-prop says the magnitude of the gradient doesn't matter. You want to get rid of the gradient scale. This is my justification for that. Because
right, yeah, I get the point, but it's interesting to see it's kind of totally different from the convex case. The convex case, like, I don't care about the magnitude of x, where I am currently. I only care about the magnitude of my gradient, like the direction I'm going to.
right.
So why do so it's really from the composition nature of the architecture, right? I guess.
I think that this consideration still holds even if you're optimizing over a single matrix. So I like if you think like the most intuitive version of this algorithm is that like you've got one matrix that you're optimizing over. Like how much can you perturb that matrix before you change its properties? And like the natural answer is that the matrix is stable up to relative change. Like if like you've got a matrix, like how much can you add to it before it's a different matrix? And it depends on how large the matrix is. If the matrix is massive, like all the entries are huge, in absolute terms, you can perturb it a lot before you can even notice a difference. But so like matrices just have this kind of relative structure. That's like, for some reason, like I don't know why, but like all this classic optimization theory or this lots of it misses the fact that, like, I would say in most problems, you actually care about the relative structure rather than the absolute structure. That for the Lipschitz smoothness assumption, you care about absolute structure, but that it seems actually that the number of problems that are captured by Lipschitz smoothness should be quite small in the space of all problems or all interesting problems. At least that's the point of view I have, is that relative is almost more natural. But let me just keep going because I don't have too much time left. So that I just introduced a per matrix relative update, but a per synapse relative update or per weight relative update looks a little bit different. And, you know, a priori, you can just try anything. So why not try an optimizer that makes small relative change per weight? So we tried that. But if you, just to show you how to interpret this, what this means is that every weight in the model, every iteration, every weight in the model either grows by a factor 1 plus eta or shrinks by a factor 1 minus eta. So this is what's referred to as a multiplicative weight update. So the kind of component-wise version of an algorithm that only is allowed to make relative change ends up being a multiplicative algorithm. And you can think of it as synapses are either growing or shrinking by a small factor. And that's just something kind of cool, but you should probably be skeptical of the next slide. But like some neuroscientists found, they looked at the way actual synapses in a real brain change over time, and they found that they change multiplicatively. So, you know, what they did is that they just, you know, they just looked at synapses over time, and they plotted the horizontal axis is the size of the synapse, and the vertical axis is how much it changed in a time step. And they found that the amount of change is somewhat proportional to the size of the synapse. And also the strength of a synapse is also proportional to the size of a synapse. So they propose that multiplicative dynamics is like what's going on, at least in this neuroscience experiment, which is kind of interesting. And it supports my claim that there's something natural about relative change rather than absolute change. But let's now move on. So the last thing I want to show you is per neuron relative updates rather than, so what this picture is supposed to illustrate is, you imagine that this is a weight matrix, which corresponds to a layer of a network. The blue thing is a row, which corresponds to a neuron's weight vector. And the pink thing is an entry or an element or a weight, which corresponds to a synapse. And the things I've told you about so far are making an optimizer that makes small relative change to a whole matrix, an optimizer that makes small relative change to an individual synapse, which is a multiplicative optimizer. And the last thing that we tried was this row-wise relative change. So if you think about what this means, it says that the weight vector for that row, the amount of change in that weight vector divided by the length of that weight vector should be set by the learning rate. So this is like a per neuron relative change. And before I just tell you more about this, there's one additional thing I want to introduce, which is we talked about weight constraints in lecture 7, and I guess they were on the homework as well. But we talked about these two per neuron constraints. So what I want to ask is, what does relative change per neuron look like? Under these constraints. And it's going to have a really simple interpretation. So if you remember what the constraints are, the first one is that for a neuron, the sum of the weights is 0. And the second constraint is that the per neuron, the squared sum of the weights is 1, or the unit length of every weight vector per neuron is 1. Sorry, the length of every weight vector is 1. So if we want to be more formal, what we're saying is that the optimization domain under these constraints, what does that look like? So the domain of optimization is the space that we're optimizing over. And if you think about it, what I want to say is that I have a neural network constructed of M neurons, each with fan-in D. Then let me call the optimization domain omega. Omega is equal to, like in mathematical notation, it's a Cartesian product of hyperspheres. So the number of hyperspheres, right? So this is the hyperspherical constraint. The number of hyperspheres is the number of neurons. So because there are M neurons, there are going to be M terms in this Cartesian product. So a Cartesian product is a product of sets. And what's the dimension of each hypersphere? The dimension of each hypersphere is, sorry, someone's texting me. The dimension of each hypersphere is D minus 2. The reason for that is because, you know, a hypersphere in D-dimensional space, so each neuron lives in D-dimensional space because it has a fan-in of D. A hypersphere in D-dimensional space is D minus 1 dimensional. That's just what you say its dimension is. And then if you apply an additional constraint, you remove 1 dimension. Like and it's actually still a hypersphere, because if you take the intersection of a hyperplane and a hypersphere, it's still a hypersphere. So we're optimizing over Cartesian products of hyperspheres. And now let's remember we're talking about relative change. What does relative change look like when you're constrained to the surface of a hypersphere? Like, I'm not sure if anyone's following, but if you know, like, yeah, just like shout out what the answer is, or if anyone has an idea. But the idea is that if you relative change constrained to a hypersphere, so this is like the situation for one of the neurons. If we induce a small amount of relative change, it's actually just a rotation. So small relative change under a hyperspherical constraint is rotation. I'm going to try and finish on time. And so we called this algorithm Nero because it rotates every neuron, and the learning rate sets the angle that every neuron turns through per iteration. So like if this is the weight vector W, then this is the weight vector W plus delta W. So it turns through a certain small angle. And what we found was that if you'd set up the optimization this way, the same learning rate worked across a whole bunch of different problems. and so there's like this almost, it's like the magic learning rate is the learning rate is half a degree of rotation per neuron per iteration. So if you think about that in like matrix terms, it's saying every row of every weight matrix in the network rotates by an angle of half a degree per iteration. And if you did it that way, you could train the network like pretty reliably without needing to tune, like even for like image classification or like natural language processing. Or so it's saying that like, yeah, that's like my claim of the lecture is that this is the right way to take advantage of the structure of the problem. Like, we're aware that we're optimizing over matrices, we're constraining the rows of the matrices in a particular way, and the optimization algorithm has this like geometric interpretation that you're rotating neurons. And if you think about, if you go back to lecture 7, remember that a neuron defines a hyperplane. So another way of thinking about it is that a network is a big product of hyperplanes. And by product now, I mean like a Cartesian product or some kind of set product. But basically, I mean, a neural network is a lot of hyperplanes, one for each neuron. And that this algorithm is just rotating hyperplanes rather than changing the length of the normal vector. And it works pretty well. So in summary, optimization theory requires a model of how the first order Taylor expansion breaks down. Popular models like mirror descent may not be well suited to neural networks, or it's at least difficult to cast them into that framework. But what at least my research has been trying to do is like directly study the perturbation properties of neural networks and come up with notions of smoothness, which are actually designed for the neural network structure. And like, hopefully the practical takeaway is that they seem to require less tuning. So next lecture, we're going to talk about generalization theory and VC theory. But yeah, I guess if there's any questions, I'm going to just stay around for a little bit. But yeah, thanks for listening.
Thanks, Jeremy.
Thank you.